Okay, today let's finish the chapter 24 and start the next chapter. Let me first hide this floating bar. Okay, so in previous lecture, we have studied the Gauss law. Gauss law is a law or equation which connects the charge and flux. So Gauss law states that the flux of a closed surface, when it's closed the surface, we can call it a Gaussian surface. So the flux, actually the electric flux of a closed surface or Gauss surface equals to the charge, actually the net charge inside the surface over a constant. So that's Gauss law. And we have done several problems to practice how to use Gauss law in the real problem. And now let's continue to use Gauss law to learn something about conductors. So first of all, let's say if we have a conductor shown in this figure, what's the electric field lines inside the conductor? Let's say if the conductor is charged. Okay, now let's see if the charges, let's say if the conductor is charged by positive charges, then first of all, what's the distribution of the charges? Is it possible we have those charges inside the conductor? Is this possible? No. Why? Because it's a conductor. Conductor means a material that the charges are free inside this material. So let's say if we have some positive charges inside the conductor, what happens? Right, they will repel each other and they have to move. And then there will be a current in the conductor. The charge will move and form the current until it reaches the boundary of the conductor that have to hold it, which is the surface. So first of all, for a conductor, if it's charged, the charge has to be on the surface. Otherwise, they will repel each other. Okay, let me erase the charges. So first of all, for conductors, for charged conductors, all of the charges has to be on the surface. Second, is there any electric field inside the surface, inside the conductor? So let's say the electric field lines might be something like that outside. What about inside? Is it something like this? Is it possible? Or is it possible to have some field lines inside the conductor like that? No, it's impossible because we can use Gauss law to do the calculation. Let's see. Let's consider about the charge, the position here. What is the electric field? So first of all, let's draw a Gaussian surface which cross the point we concern. So inside the Gaussian surface, what's the net charge? 0. So it's 0. If you draw arbitrary or any surface that is inside the conductor which go through the concerned point, you will see the net charge inside the Gaussian surface is always 0. So if there's no net charge, then the electric field line at this point simply should be 0. So this is the first way to understand zero electric field. Second way, if there is an electric field, we know in the conductors are composed by, for example, let's say metal. Metal is usually conductors. It's composed by electrons, protons, and let's say neutrons. Usually the electrons are free. If there is a electric field line, the electrons will move. So they have to move until the electric field line is canceled. So for those reasons, inside a conductor, there shouldn't be any electric field lines. Okay. Okay, so that's inside. Now let's see outside. Outside the out of the conductor, is there any field lines? Is it possible to have field lines outside? Yes, because we mentioned that the charges should be distributed on the surface of the conductor. Therefore, there will be some electric field lines out of this conductor. The external electric field right at the surface of conductor must be perpendicular to that surface. So if we take a look at the field line here, you will see it's perpendicular to the surface. Is it possible we have a conductor? I'll make a arbitrary surface of conductor. Let's say this is conductor. Is it possible the field line is not perpendicular to surface, but it's in a tangent? It has a tangent component to the surface. Is it possible? It's impossible. Why? The same reason. Let's say, let me erase this part. Let's say if we have field line going in this direction, which has a perpendicular and a tangent components, let's divide it into two components. In perpendicular and tangent components. If it has a tangent components of the electric field lines, what happens? The charge will move along the surface, because now you have an electric field going to the right side, then the charges at this position will try to go to the right side. It cannot go out of the surface, which is perpendicular direction, but it can go along the surface, which is the tangent direction. So the same reason, when there are some net charges distributed on the surface of a metal or conductor, the electric field lines has to be perpendicular to the surface. Otherwise, the charges move. They will move and keep moving until at every point the field line is perpendicular to the surface. Then it will stop. It will be in an equilibrium state. So due to that reason, if there were to have a tangent component, it would exert a force on the surface, charges, and move it along the surface. The conductor would not be in electric equilibrium. When it's in an equilibrium state, all the field lines has to be perpendicular to the surface. Okay, so the field lines should be 0. We have talked about that. Okay, So that's some basic, let's say 3 basic rules for charges on the conductor. First of all, charge. For the conductor, what's the charge distribution? What features does the charge distribute on the conductor? Right, it has to be on the surface. Second feature is about the electric field line inside the conductor. So inside the conductor, what direction should be the electric field line? Perpendicular inside the conductor. What direction should the field lines be? Should they be perpendicular to the conductor surface? Actually, there shouldn't be any electric field lines inside the conductor. So third feature, outside the conductor. What are the directions of the field lines outside the conductor? Exactly, perpendicular or normal direction. And we have explained the reasons. Now let's do a calculation for electric field lines outside the conductor. A Gaussian surface extending through the surface of conductor has a flux only through the outer surface. Let's say we have a conductor here, and of course we have a lot of field lines outside. Now let's calculate the electric field lines or electric field. So first of all, let's take a very small piece of the conductor surface. Let's say the area is A. And then what we can do is we can make a Gaussian surface. First, we set up a cylinder which is perpendicular to this piece of surface. And then we'll have 2 ends. One end is outside, the other end is inside. So first of all, if this piece is small enough and it's perpendicular to the surface, first of all, what is the flux? Let's say going through the side surface of the cylinder or the curved surface of the cylinder. 0. Why? Exactly. So because of we have talked about the field lines outside, it has to be perpendicular to the surface. And now if you draw, let's say a cylinder, and the cylinder is perpendicular to the surface, then the field lines shouldn't go out of the curved surface. So on the curved surface, the flux is 0. And now you have 2 other surfaces. One is the tip at the out of the surface. The other one is the other end inside the surface. Let's talk about them one by one. First, inside the conductor, you have a surface which is A. What's the flux going through that surface? 0. Why? Right, because we mentioned inside the conductor, no field lines. So the flux should be 0 inside. And outside, it's non-zero, it's not 0. So you have E, you have A, but E and A should be in the same direction because they're all perpendicular to the surface. Then A times E becomes the total flux for the entire Gaussian surface or the cylinder, because all the other surface for the cylinder, the flux is 0. Only at this surface, the flux is A times E. It should equals to the net charge that is wrapped by this cylinder. So the net charge wrapped by this cylinder is here actually. This small piece of surface on the conductor, it has some charges, and it can be calculated by eta times A. A is the area on the surface, and eta is the density. So eta A is the charge. Then we can use Gauss law. Gauss law states that the net flux equals to Q over epsilon 0. E is the thing we need to calculate. A, we don't know. It's a very small surface. Let's just say A. And Q in, it's eta A over epsilon 0. Epsilon 0 is constant. Then A and A are canceled. Then you will have E surface equals to eta over epsilon 0. So that's the electric field out of the, let's say, conductor surface. Okay, so that's a problem we have solved for the electric field on the conductor. So this is the equation. You can use it in your homework and exams. Okay, so far, do you have any questions? If no questions, let's take a look at this quick check question. Let's see which option do you think is right? Did you get your answer? Okay, let's see. So who's going to choose A or B or C or D or E? Okay, so what's the keyword? Metal. So if it's a conductor, if it's a metal or conductor, what is the field line inside it? Zero. No matter what happens inside a conductor, the electric field should be zero. What about? Yeah, that's a good suggestion. Now, let's move. Let's say if we move this charge to a very closed position at the surface, very close, but not touching the surface, then what's the electric field here? Still zero. It doesn't matter how far it is, it's just zero. What about if I put a positive charge here, but a negative charge here? What happens to this point? What's the electric field? Still zero. So no matter what you do, if the field lines, the charges are outside conductor, no matter what you do, inside the conductor, simply the electric field should be zero. Okay, now let's make it even a little bit more complicated. What about if our conductor is not a solid conductor, but there's a cavity inside the conductor? Now the same conductor, but you have a cavity here. So first of all, what's the charge distribution for a conductor which has a cavity, but also have some net charges, let's say positive charges? Is it possible that the charges distributed on the surface outside and also surface inside or the surface around the cavity? Is it possible? Exactly. So this is impossible because it's metal, it's conductor. No matter metal or other material, if it's a conductor, it simply means, let's say, the charges are free to move. Now let's take a look at this charge and that charge. They are free to move and they repel each other. When they repel each other, they have to move as far as possible. What's the farthest place they can be? The outside surface. Then they will move to the outer surface as far as possible until they reach the boundary, because they cannot jump out of the surface. They can only move to the surface, but not out of surface. So it's impossible. First of all, it's impossible to have surfaces, to have charges distributed on the inner surface or surrounding the cavity. They're all on the outer surface. Second, what is the electric field, let's say, in the conductor? Is it something like that, or maybe like this? Is it possible? No. Why? Yep. If there's a electric field, the charges inside the conductor will move. So there shouldn't be any electric field inside. Furthermore, let's see. Is it possible to have some electric field inside the cavity? Why? No charge at all. So all the charges are distributed on the outer surface. So inside surface, there's no any charges and there's no any electric field. Okay, so that's the two important features for a cavity in a conductor. For cavity in a conductor, first of all, on the surface of the cavity, then the charge distribution is zero. There is no any charge distributed on this surface. I mean, the surface of the cavity. Second, inside the cavity, there shouldn't be any electric field. Okay, because of this feature, then we can use this feature to do some practical things. For example, a Faraday cage or any metal box. First of all, if we have external electric field, which is shown here, they're always going from left to right. That's an electric field. If you put, let's say, a metal box or a piece of metal with a cavity, you can consider a metal box to be a whole piece of metal with a cavity, right? That's the same thing. Now, if you have a metal box inside, then what happens? The electric field inside this box should be zero. The same reason for this. So in the cavity, the inner surface shouldn't have any net charges, and inside the cavity, there shouldn't be any electric field. The same thing here. Because this is metal or conductor, so inside on the surface of the inner cavity surface, the charge should be zero. All the charges should be distributed out on the outer surface, and inside the cavity or inside the box, the electric field should be zero. So it's a very good way to screen the electric field. Let's say if you have some external electric field, you want to just screen it. The best way is just use a metal box. So the same thing for many other electric or magnetic signals. For example, your cell phone, if you have a box which is made by metal, it simply can block or screen the signals outside the box. If you put your cell phone inside, it will not receive any signals anymore.
So kind of like a Faraday cage.
Exactly. Yes. So a metal box is considered to be a Faraday cage to screen the signals. Actually, it's not even has to be a real box. Let's say it doesn't have to be a solid box. For example, if you have some holes in the box, it's okay. So small holes cannot let the signal come into the box, or even a mesh of box. It's not solid piece of box, but it's made by metal meshes. It can also screen the signal. Okay, now let's see an even more complicated case. Now you have conductor with a cavity, and also you have a charge, a net charge inside the cavity. Then what happens? Let's say if you have a net charge, which is positive charge put in the cavity, it will attract the negative charges from the conductor and repel the positive charges from the conductor. And therefore, once you put a net charge in the conductor, you have negative charges on the cavity surface and the positive charges on the outer surface. And this is called induced charge. Now let me ask a question. Do you know the quantity of the induced negative charges distributed on the cavity? Let's say if you have the point charge to be Q, what's the induced charge surrounding the cavity? Negative Q. Why? Right. So it has to be the same, but opposite signs of the charge as Q. So that when you draw a Gaussian surface like this, the let's say the net charge inside the Gaussian surface should be 0, so that the electric field should be 0. Because we know in a conductor, inside the conductor, the electric field should be always 0. So that the net charge need to be -0 on the cavity surface to balance the net charge Q. In this way, no matter which kind of Gaussian surface you draw, as long as contains a cavity, the net charge is always 0, and then the flux is always 0, so the electric field is always 0. Okay. Okay. Now let's check this question and see which answer is correct. Did you get your answer? Okay, let's see. So who's going to choose A or B or C or D? Okay, the answer is C. Why? Because as we said in the previous example, on the surface of the cavity, it has to be, here it's +3, then on the cavity, it should be -3. But totally it's neutral. The metal is neutral. So if you have -3 in the cavity there, then it has to be +3 on the outer surface or exterior surface. Okay, good. Okay.
What if the metal is
Oh, then that's a good question. Let's take another example. Now you have a not neutral metal, but it's let's say Q. Or let's do not make it Q, but make a real numbers. Let's say it's +2 nanocoulomb, and of course it has a cavity. So the net charge of this thing is 2 + 2, and then once I put a net charge inside the cavity, which is again +3 nanocoulomb, then what's the net charge on the outer surface? Once you put a charge in the cavity?
the 5?
Right. Why? Because this charge in the cavity, it will generate some induced charge, which is -3, right? When there's a -3 generated on this side, there must be a +3 repelled on the outer surface to balance the inner surface. Then totally on the outer surface, you will have 5. Okay, good. Let's see. Okay. Okay, that's it. Then that's all for our chapter 24. So far, do you have any questions? If no questions, the chapter 22, 23, 24 will be what we need to cover in the midterm. And the midterm will be on 29th, right? Okay. The second week after the fall break, it's 29th. Okay, let's take 5 minutes break and we'll come back. And then let me hide the floating bar. Okay, now let's start our chapter 25. So in this chapter, we're going to learn something about the electric potential and electric energy. So first of all, let's talk about potential and energy. Which types of energy have you learned before in physics? Kinetic energy.
I heard about chemical
Chemical energy, right. Is there any other types of energy?
potential.
Potential energy. So there are several different types of potential energy. For example, gravitational, right? When you lift something up, let's say my mouse, when I lift it up, the higher I lift it, the more gravitational potential energy it has. Because if I drop it, when it's on the floor, the higher it is, the more energy it has. Which type of other potential energy have you ever learned or know? Spring. So if I have a spring, if I stretch it or compress it, that's an energy. Because when I release it, it will just release the energy. It can do some work. That Okay, so today we're going to learn some more potential energy, which is electric potential energy. So before we learn it, you can imagine, first of all, if you have two positive charges, what's the force between them? What's the direction of the force? Is it repelling or attractive? Repelling. What happens if you press them and make them getting closer to each other? That's a potential energy. You need to do work. You need to push them hard and push them together. Once you release it, they will move away. And when they move away, the potential energy becomes kinetic energy, just similar as the spring. When you push the spring together, then when you release it, it can convert the elastic potential energy into kinetic energy. So the same thing for electric potential and electric energy. But before we start the electric potential or electric energy, first of all, let's review a little bit of first kinetic energy. Do you remember how to calculate kinetic energy? It's shown here. It's a 1/2 of mv squared. So m is the mass and the v is velocity. So it simply means the bigger mass or heavier object you have, the more kinetic energy you have, and the higher speed you have, the higher kinetic energy you have. That make a lot of sense, right? If you drive a car, if the car is heavier, then compare with another car which is lighter but with the same velocity, of course the higher car or the car with a greater mass will have more kinetic energy. It's more difficult to stop it. And then the same car, if the same car is driving in a low velocity and a higher velocity, of course, a higher velocity will have more kinetic energy because it's difficult to stop. But with the low velocity car, it's easier to stop it. Means the kinetic energy is less. Then that's the kinetic energy. Then let's talk about the potential energy of a system. Usually we use U stand for the potential energy, but K stand for kinetic energy. The change in potential energy delta U is -1 times the work done by the interaction forces. Let's take an example of one potential energy, which is gravitational potential energy. The change in potential energy, let's say if I move this mouse from this level to this level, so I move from here to there. First of all, what is the delta U, or the change of gravitational potential energy? Is it positive or negative? Positive, because it's getting bigger. And then what does the gravitational force, what is the work that is done by the gravitational force? Is it positive or negative? It's negative, because the displacement from here to here is positive. Let's say going up is positive usually. Usually we define positive direction to be going up, and in horizontal direction we define positive direction to be to the right. So now the displacement for this mouse is going up, means positive displacement. And what's the direction of the gravitational force? It's going down. So a force going down, displacement going up, it's dot production to calculate the work. Work equals to force times, not time, but dot product the displacement. And they have angle of 180 degrees. Cosine 80 degree is -1. So the the gravitational force has done the work of negative, so that your delta U is positive. If all the forces involved are conservative forces, such as gravity or the electric force, then the total kinetic energy is conserved. It doesn't change in time. For example, if I release the mouse from this height, it will fall down, right? When it falls, there's only one force doing work, which is the gravitational force. And the gravitational force is considered as a conservative force. So if there's only a conservative force, in this case, a gravitational force doing the work, then the K plus U is conserved. So from here, the lower position, from above to below, the gravitational energy is losing, right, from high to low, but the kinetic energy is gaining. It gains more kinetic energy, so that K plus U is conserved, or it's a constant. Okay, let's recall how to calculate the work. The work can be calculated by work equals to force dot product delta R, or displacement. Keep in mind that here it's a dot product. Dot product of two vectors equals to a scalar, which is the magnitude of F times magnitude of displacement times cosine theta. Theta is the angle between them. And then because of the way we calculate the work, or the way we define the work, then in the first case, if theta is 0, which means they're in the same direction, the force and displacement are in the same direction, then the work equals to F delta R. It's positive because they're in the same direction. Second case, if the force is perpendicular to the, let's say, delta R, or displacement, then theta equals 90 degrees, then the work is 0. And in another case, if the force and displacement, they're in the opposite direction, which means theta equals to 180 degrees, then cosine theta equals to -1, then the work equals to a negative number. So let's do a little bit practice for the work calculations. Now, for example, if I have a cell phone here, I can move to there because I have to speak to the laptop. So I'll try to, okay, I need a table. Or I can use a chair. Let's say we have a chair here. So if I am trying to push the chair, I need to push it in a horizontal way from your left to your right side. If I push it this way, let's say if I push it from here to there, which has 2 meters. When I push it 2 meters, so what type of, or what kind of work did I do? Do I do let's say a positive work or negative work? That's a positive work because my pushing force is to the right and displacement is also to the right. So it's positive work. What does the friction do? What type of work does the friction do? Positive or negative? Negative, because it's in the opposite direction. So what type of work does the gravity do? 0 because the gravity force is going down and we're moving it in a horizontal direction. So the displacement and the force here, the force is a gravitational force. They're in perpendicular directions. Or theta is 90 degrees, then it falls into the second case, the work should be 0 because cosine theta is 0. No matter how long you push it, how hard you push it, the gravitational force doesn't do any work. What about if I lift it up from a lower position to a higher position? When I lift it up by, let's say, 0.5 meters, then what type of work did I do? Positive or negative? Positive, because I push it, my force is going up and the displacement is going up. So it's positive work. Then what type of work does the gravitational force do? It's negative. Negative. The gravitational force is going down, but the displacement going up, then the work is negative. Let's say when you're in the elevator, when you're moving up, what type of work does the elevator do to you? Positive, because the elevator is moving up, your displacement is up, and the supporting force is pushing force is also going up. When the elevator is moving down, what type of work does the elevator do to you? So first of all, what's the direction of the force? So what direction is the supporting force when you're standing on the elevator? It's still going up. It cannot be going down. Going down means something is pushing you or dragging you. Elevator doesn't push you down or drag you down. It's holding you. It needs some force to hold you. If there's no force hold you or support you, what happens? You'll be in a free fall. It's a fast. But in order to make you safe, to make you going down smoothly or in a, let's say, uniform velocity, the elevator has to support you. So the force is still going up. Right. So when it's moving down, the elevator is doing some negative work to you. What about the gravitational force? It's doing some positive work because gravitational force is going down and your displacement is down. So it's a positive work. Good. So we have reviewed a little bit about the work. Now let's move on to the calculation of gravitational work. Every conservative force is associated with a potential energy. We call some force to be conservative force. For example, the spring force or gravitational force. And later on, you will learn electric force, electrostatic force or electric force. So those forces have feature, which is when those force is doing some work, then some energy will be changed between a potential work and other type of work. For example, if there's a gravitational doing some work, let's say when you drop something down, then if there's only the conservative force, in this case, the gravitational force doing the work, then the potential energy, the gravitational potential energy is converted into kinetic energy. In the case of gravity, the work down can be calculated by mgy initial subtracted by mgy final. What is mg? That's the gravitational force. M is the mass. Mass times G is the weight or gravitational force. Gravitational force times Y, which is the position in your vertical direction, then that's the potential. Then Y initial subtracted by Y F, then you get the potential change. Potential change is the energy. The change in gravitational potential energy is delta U equals to the work has done by the U, but negative sign, where gravitational energy equals to the reference, let's say gravitational potential equals the reference potential times mgy. Mg is the weight, y is the distance it moves in vertical direction. Okay, now let's go through some quick check questions. So first of all, which one has more gravitational potential energy? So who's going to choose rock A or rock B? C? D? The answer is B, because if they have the same size or if they are the same rock, the higher it is, the more energy, the more gravitational potential energy it is. Okay, very similar to gravitational energy. For gravitational energy, the main reason for gravitational energy is the gravitational force. For gravitational force, if you put an object in a gravitational field, then it will exert some gravitational force going down. Similar to gravitational force, let's talk about the charges in electric field. If you have a charge which is, let's say, which is inside the electric field, it will have some forces on the charge, which is electric force. So very similar to gravitational forces. Those charges are tending to move to the left in this case. And then when it moves, the electric field or electric force will do some work. And then once those type of work is done, the potential of the charge will be changed and other types of energy will be gained, which is in this case, the kinetic energy. If you release a charge and the charge moves in this electric field from the right side to the left side. So a positive charge Q inside the capacitor or inside the electric field speeds up when it falls toward the negative plate. It's simply just the same as object falls to the ground in a gravitational field. There is a constant force, which is F equals to QE. That's the definition of E. Electric field means the force over Q. So the force equals Q times E. So there's a constant force F equals to QE in the direction of the displacement. The work done can be calculated by QE. Let's say here it's S initial and S final. Then the work has been done is QE times delta S, which is S initial subtracted by SF. The change in electric potential can be calculated by the work that has been done, but negative sign. Then if we define, let's say, if we define one position, could be a reference position, let's say here, could be a reference position, and at this position, the electric potential is 0, then electric energy equals to U0 plus QES, which means the distance of the charge movement times the force. The force is QE. So that's the definition of electric potential energy. So in this example, okay, let's see next example. In this example, A and B, which one do you think has more energy? Okay, let's try. So who is going to choose option A or B or C or D? Okay, let's go back to this example, the gravitational potential. So here is my mouse. I put it here. This is position 1. This is position 2. If I release the mouse, what direction does the mouse go? Going down, because it's trying to find out the lowest energy position. So that's nature. So for an object in the case in nature, it's always trying to find the lowest energy position, such as water. The water always goes down because the energy is lower. Now let's go back to this example. If I have a charge C, let's say here, this is my charge C. I put it here, it's a positive charge. If I release it, which direction does it go? Going up. Then which direction has lower energy? Up. So in nature, the object always try to go to lowest energy. So here, now let's compare A and B. Which one has lower energy? B. So A has higher energy. Okay, let's stop here and we'll continue on Thursday.